Okay, so thanks everybody for attending the next talk. So our next speaker is Monica Winkelmeyer from Los Andes in Colombia. She'll talk about the min-max principles and bounds for eigenvalues of one-dimensional Dirac operators. So thank you for giving us this great talk, Monica.
Yeah, so good morning, everybody. And thank you very much to Jonathan, Christoph, and Marina for putting this event together. So yeah, I want to speak about the min-max principles and bounds for the eigenvalues of the one-dimensional Dirac operator. So maybe first let me introduce the object that we want to talk about. So the Dirac operator in one dimension looks like a block operator matrix, or a sum of two block matrices. So on here we have on the off diagonal first derivative. Once it's positive, once it's negative, so that the thing is symmetric. And then here we have a matrix which has all sorts of operators in it. This then would be something like the potential. So we can also write this operator here as the part with the differentiation, and here the potential. And we will always assume that our potentials are bounded. So these m's here on the diagonal usually have some interpretation of mass. This is some mass term. And so, as I said, we want that our functions m1 and m2, and also the w on the off diagonal, are bounded, measurable, and real valued. And we also want that the mass functions, the things here on the diagonal, that they are sort of separated. So when we plot this m1 function, the positive one, and the minus m2, and then we want that the infimum of this m1 is strictly larger than the supremum of minus m2. Or this would then be the infimum of m2. So the signs sometimes are a little bit confusing. But so basically what we want is, if we plot the functions which are on the diagonal, then there should be left some gap between them. And we always can put 0 in this gap, because we just like sum a multiple of the identity to our operator, and then basically the things just get moved up and down. So this is not a real restriction. Okay, and we also want that the limits of all these functions that appear here exist. So in particular, this 2 by 2 matrix V of x should have a limit. Because then we can say something about the spectrum of our operator. So we calculate the limit. We assume that it exists. Then in the limit, this is just a 2 by 2 matrix. We calculate the eigenvalues for both limits. And then we get something like this. Let's say these green dots are the eigenvalues for the potential when x tends to infinity, to plus infinity. So we get 2 points. We do the same thing for x tending to minus infinity. We get another set of points. It could be interlacing. It could be something like this, whatever. And then of these points, we pick from the 2 smaller eigenvalues, we pick the larger one. And from the 2 larger eigenvalues, we pick the smaller one. Something like this. And then this point here, the larger of the small eigenvalues, we call lambda e minus, and the other one is lambda e plus. Something to note is that these eigenvalues will always be, the larger one will be larger or equal than m1, and the smaller one will be less or equal than minus m2. Because this is when we take x to plus infinity or to minus infinity, then in the matrix here, we just have the limits of the m's, and these limits are larger than the infimum of m1 or smaller than minus m2. And these, let's say, perturbation here in the off diagonal, they just push eigenvalues further apart. Sort of, something like this. So, well, anyway, this happens. And then if we look at the operator in this general version, then we can say several things. Again, with all our assumptions that these functions here are bounded, they have well-defined limits for x to plus and minus infinity, then we know that our operator t is in the limit point case both at plus and minus infinity. This means that if we want to have a self-adjoint realization of this operator, then we do not have to impose boundary conditions. There's only one self-adjoint realization of this operator on the real line. And the domain which makes this operator self-adjoint is, well, the natural one, h1 of r, direct sum with h1 of r. This is because we have here two components. I should say that, of course, we're working in the Hilbert space L2 of r squared. So L2 of r times L2 of r. From all of this, we also get that eigenvalues of t, if they exist, are simple. We also get, and this is now why these lambdas from the slide before are important, we also can localize the essential spectrum. So if we only have what I just said, then we know that the essential spectrum is contained in minus infinity to this lambda e minus, union with lambda e plus to infinity. And now, since we had this assumption on the infimum of M1 and the supremum of M2, we know that there's always going to be a gap, because then always this lambda e minus will be strictly less than lambda e plus. And if we assume slightly more, then we even get equality. So the essential spectrum is equal to the union of these two semi-bounded intervals. So the picture is like this. Here we have the real line. We know that from minus infinity to lambda e minus, everything is essential spectrum. It can even be shown, so this was already done by Weidmann in the 70s or so. So we know that, here we even have only absolutely continuous spectrum, so there are no embedded eigenvalues if the potential is nice enough. And then again, here from lambda plus to plus infinity, also everything is essential spectrum and there are no embedded eigenvalues. So eigenvalues could appear only here in this gap from lambda e minus to lambda e plus. This is the only place where really eigenvalues could appear. So let us first look at a very special case. This is when m is constant. When m is constant, then we can just take the square of our operator, and then we get something like this. The good thing is now that on the off diagonal we only have 0, so this is just a direct sum basically of two operators. Of course, one needs to take care about domains and stuff like this, because here we have a product of two unbounded operators and the same here. But let's say, assuming everything works well, then by squaring we just get this diagonal operator. And the good thing is that these diagonal operators, both of them are bounded from below. They are different because basically we have here plus derivative and here minus derivative, and in the second line here it's the other way around. But one can also see that roughly this is just a product of something like an operator with its adjoint, and here's the other way around. So we always have non-negative operators, actually positive operators, if this m here is really larger than 0. Okay, this is good because then we know that again, the essential spectrum is something like it starts somewhere and then it goes up to plus infinity, but the operator is semi-bounded from below. And for the eigenvalues below the essential spectrum, we actually can apply the classical variational principle, which gives us the eigenvalues below the essential spectrum. This was done actually in a paper in 2014 by Jakubski and Grejčerik. They then gave lots of criteria when eigenvalues exist and where they are roughly. So on the next slide, I just want to give a brief recap of what the classical variational principle says for semi-bounded operators. So let's say we have a semi-bounded operator A, then one can form the so-called Rayleigh coefficient, a Rayleigh quotient. This is this. So you take x in the domain of A, and then you just calculate ax in a product with x. And this is, you divide by x squared. This is just for normalization. You could also just restrict yourself to vectors x in the domain of A, which are normalized, and then you don't need this term downstairs here. Okay, and now with this quotient, one can describe all the eigenvalues below the central spectrum of the operator A. And this works like this. One takes n-dimensional subspaces in the domain of A, and then within such a fixed subspace, one takes the maximum over all these quotients. And then one takes the infimum over all possible subspaces that one can choose. So for example, if n is equal to 1, then this maximum here doesn't exist, and one just takes the infimum of all the inner products of ax with x. And this gives the first, so the lowest eigenvalue. And then using a spectral theorem, one can prove that this here gives all the eigenvalues below the central spectrum. If we have infinitely many eigenvalues, then these beta n's tend to the boundary of the central spectrum from below. If you have only finitely many eigenvalues below the central spectrum, then this Bn will be equal to the lower bound of the central spectrum, if n is large enough. Okay, now let's think of this a little bit differently. So what we do is we fix a vector x in the domain of A. We want it to be different from 0, so just like upstairs here. And now for this fixed x, we define a function. And this function goes from R to R. And this is just, we take a minus lambda x, comma x. Okay? And then we look at the zeros of the thing. So for a fixed x, there exists exactly one lambda, such this t of lambda is equal to 0. But this is then exactly, I mean, this is just this inner product that appears here, right? So if we now denote the 0 of this function t lambda x by p of x, then we can plug it in upstairs here, and then beta n can be written just as the infimum over all these subspaces of the right of n-dimensional subspaces and then inside these subspaces you take the maximum over all these zeros, right? So I plotted here, I mean, in this case, this function t lambda is just a decreasing linear function. And you can see here for different x's, there are different, different zeros, and then you just take the infimum of all these zeros for the first eigenvalue. Okay, and now what we will do, or what has been done, is that this idea that one has to take this inf of max of such functionals can be generalized to functionals which are a little bit more complicated, but which then allow us to get some information about other type of spectral problems. Okay, so let's go back to our original operator, this Dirac operator, which is this 2x2 block operator matrix. If m is not constant and we try just to square it, then we don't get anything diagonal. It looks actually even worse than before. If we try to apply the variational principle directly to our block operator matrix T, then this is not going to give us any information, because if we try to do this inf and maximum procedure, then we just always get minus infinity, and this doesn't give us any real information. Okay, but there exists a generalized variational principle which works very well for block operator matrices, and this is what then last year, in a paper that appeared last year, I applied with Daniel Sanchez Mendoza to say something about our Dirac operator. Okay, so let me first talk a little bit about this generalized variational principle. So again, this works very well for operators which have a given block matrix structure. This was introduced 20 years ago or so by various authors, Binding, HV, Heinz Langer, Matthias Langer, Christiane Dretter, Margarita Kraus worked on this too. So how does this work? So we have here our block matrix. Again, in our concrete case, we have this differential operator on the off diagonal. Then here we have potential, and now it's better. It's a good idea to write it just as here we have this m1 and minus m1 on the diagonal, and we put together these off diagonal elements as first derivative plus w minus first derivative plus w, right? And then we can see that the entries on the diagonal, on the off diagonal, sorry, they're adjoint to each other, as of course it should be, because our operator T here is self-adjoint with the correct domain. Okay. Now, with this, we define the so-called Schur complement. Again, remember that we said that everything here in this potential is bounded. So certainly also the spectrum of this minus M2 is bounded. And then we take lambda larger than the spectrum. So, and this supremum of the spectrum of this minus M2. In this case, the operator minus M2 minus lambda is invertible. And then we can write down this object here. So this is just, it can be thought of something like a perturbation of M1 minus lambda, because here we have this M1 minus lambda, and then we subtract something which has to do with the off-diagonal elements, and here this resolvent of this M2, which exists by the choice of our lambda. Okay, so where does this thing appear? Okay, of course, it's a bit, well, not so nice, because on here, this second term here is a product of unbounded operators, and then you always need to be very careful with domains and such things. Okay, so why are we interested in this Schur complement? This comes from a factorization of our matrix. So if here we have T minus lambda, then basically we have here on this, in this entry here, we have minus M2 minus lambda, and we know that the thing is invertible. And then just as in linear algebra, we can use this entry here and do row transformation and column transformations so that the diagonal up here and the diagonal off-diagonal element B star here, they disappear, right? So this here is the thing which makes the B upstairs disappear, and the matrix on the right is a column transformation. It makes the B star to the left of minus M2 disappear. And then on the diagonal, we are just left with S of lambda, and well, the thing that was there before, minus M2 minus lambda. Now, by the choice of our lambda, we know that this entry here is bijective, because lambda is in the resolvent of minus M2. So this here is bijective. The matrices on the right, when viewed in the correct spaces, there are also bijections between the series of bijection between the domain of the direct sum of B star plus L2 to, where does this go? To the domain of this operator, and then this operator on the left is a bijection from the range of the operator in the middle to L2 times L2. So the thing is that if we want to know whether or not the matrix on the left is injective, we can concentrate on the matrix in the middle, because the things, the first matrix and the last matrix, they are injective. So injectivity is only seen here in this matrix in the middle. But again, the term downstairs here is a bijection. So we only need to see whether or not S of lambda is bijective. If it is not injective, then the whole thing is not injective, and then we know that we have an eigenvalue of the operator that really interests us. Okay, so resuming what I just said, if our lambda is larger than the spectrum of minus M2, then we have an eigenvalue of our Dirac operator if and only if 0 is an eigenvalue of our Schur complement function here. Okay? So when you're interested in, if you're interested in the eigenvalues of the Dirac operator, then it is sufficient to find the point spectrum of S. Just to recall, a point is called an eigenvalue of operator pencil. So this S here is an operator function, if and only if 0 is an eigenvalue of S evaluated in this lambda. So this is what we have to do. Okay, and how can this be done? And here again now we see a where this idea of such functionals appear. So we define a quadratic form for each lambda. So for fixed x, we get a function which goes from R to R, and to every lambda. So if our x is in the domain of S of our Schur complement, then it's just this inner product, S of lambda, xx. Remember that for the classical variational principle, this function here was just a minus lambda. And now it's a little something bit more complicated. So again, here we have this linear term in lambda, but now it's a little bit more complicated. Now we would like to have, we would like to see that our form is, the domain of our form does not depend on lambda. How can we see this? Well, we just say if our x is not only in the domain of S, but in the if it's, well, it suffices if x is in the domain of B star, then in this formula here we can put this B on the other side, and we get actually a quite nicer formula, which is m1 minus lambda xx. So this would sort of resemble the thing which comes from the classical variational principle. And then we get this extra term here. And we can see that the domain of S, so let's say the natural domain of our function, of our form S here, is independent of lambda, and it's equal to the domain of B star. Okay? And this form is closed, lower bounded. It's quite nice for fixed A. Okay, so again, for fixed x, we find that this object here is decreasing in lambda. Why? Well, because we have here this minus lambda term. This term here tends to 0 when lambda becomes large, because this is a resolvent of something nice. So this here is something like 1 over distance of lambda to the upper bound of the spectrum of M2 minus M2. And also, again, because we have this linear term, this minus lambda term in our formula, we know that this here tends to minus infinity when lambda tends to infinity. What does this mean now? This means that for fixed x, this thing here, seen as a function from R to R, has at most 1, 0. So basically, again, we have this same nice property that we had for the form that we got from the classical variational principle. And then one can prove that actually the nth eigenvalue of S below its essential spectrum is equal to this thing here. And this actually looks just the same as we had for the classical variational principle. We also had a maximum of, well, actually supremum, but one can show that this really is a maximum, the maximum of the 0 of a certain functional, and then we have to minimize over all possible eigenvalues, subspaces of the domain of our functional. There is a slight difference here. Sometimes one has to modify the dimension a little bit. This n0 is an index shift, which basically happens if there are x's for which our function already starts below 0. So basically, there may be sort of a subspace that we have to take out. So here's just the general hypothesis for the variational principle that we are using. This comes from, I took it from this paper. This is Eschwelanger, but it also appears already here in Binding Eschwelanger. So we need that our operator function is continuous in the generalized sense, which means in the resolvent sense. we need this the negative dimension, well, the dimension of the negative subspace of S of gamma for at least some gamma is finite. This dimension here has to do with the index shift that sometimes is needed to accommodate for certain dimensions. We also need the domain that the domain of our functional is independent of lambda, and we need that this S here for fixed x is continuous and decreasing. And as I just said, for our operator, we have all of this, so we can apply this variational principle to say something about the eigenvalues. One can even go a step further, and one can describe this zero also again as a variation over something. Just quickly, I mean, we did not really use this, but it's a nice thing that they showed. This is we take such column vectors in the domain of T. Remember, T is this 2 by 2 matrix, so elements in the domain are column vectors like this. And then we build this 2 by 2 matrix. This now is a 2 by 2 matrix in the complex numbers. There are no operators anymore. Every entry here is a complex number. And then one calculates the eigenvalues. One takes the larger one. And then the zero that we want for this fixed x here is then the maximum over all these eigenvalues when y varies in the domain of B with norm equal to 1. And then in the end, we get this triple variation principle, and this then would allow us to give bounds for this lambda n if we can sort of say something about these min, max, max. Okay, now let us go back to our one-dimensional Dirac operator and see what these principles can tell us about eigenvalues or spectral free areas of our operator. And this now is joint work with Daniel Sanchez Mendoza. So again, I wrote down here our operator that we are interested in. And if we write down the Schur quadratic form for lambda larger than the spectrum of M2, then we get just something like this. This was this M1 minus L. This is basically this entry here, minus L, and then minus the perturbation. Well, minus and minus becomes a plus, and then here this M2, this was minus, so originally this was minus M2 minus lambda. The minus goes out, this gives you the plus. And then remembering that the M1 and M2 operators are just multiplication operators, we can write this here as this super large integral. We can take out this M2 plus lambda inverse. This is just multiplying by 1 over M2 plus lambda. And then we can write this as one quotient. And here we would then get the product of the two, which then we can unite with W, which comes from this B star and B star term. So basically here we get minus the determinant of V minus lambda. V is this matrix here, which contains our multiplication operators. We get a term F prime square, and then we get here a weird term, which is the real part of F with F prime. So this is our Schur form. And again, for fixed F, we are interested in the zeros of the thing, right? So what we want, we know from the principles that I just showed you that the eigenvalues of T in this interval here from minus M2, which is the upper bound of the spectrum of minus M2 of our operator minus M2 here, up to the lower bound of the central spectrum of T, we know that the eigenvalues are equal to this min-max principle thingy here, where this PF is the unique zero of S for fixed F in this interval here, in case the zero exists. Okay, now if we apply this, then the first theorem that we get is the following. So just a little reminder. Our M functions, they look like this. We have a gap between them, which allowed us already to say that the central spectrum does have a gap. It can be larger than the gap between these two m's, because we also have contributions from the W, and also only the behavior at the limits, plus x2 plus and minus infinity, are important. So here we get this gap in the central spectrum. And now, using our principle, we can already say that actually all of the space between minus m2 and m1, so basically the gap between these two functions here, this belongs to the resolvent set of our operator. And then we only have two regions left where eigenvalues could appear, either between lambda e minus and minus m2, or between m1 and lambda e plus. How can this be proved? Just to give you an idea how this works. Again, remember that what we need are the zeros of our functional of this here. And in this case, we just take, so we take lambda between minus m2 and m1. And if you take such a lambda, if we plug this in here, then we can estimate, we can say, okay, this here is always going to be positive. Also, the things that come here from this m2 will always be positive, actually strictly positive, if lambda is in this open interval, which means that this functional for any f in the domain of B star will always be positive, which means we cannot have any zeros here, which means that this is free of spectrum. There is no spectrum of the Dirac operator there. We can also use the principle to say something about the existence of eigenvalues. Again, we need zeros of something like this. We fix f, and then we let lambda vary. And if we have zeros, then this tells us something about the eigenvalues. And the theorem is like this. If there exists a f0 in the domain of our quadratic form, different from 0, and if we can find some lambda 0 in this interval here, such that this is less or equal than 0, then we know that our operator has at least one 0 between m1 and this lambda 0. And the reason is simply because if we plug in this lambda 0, if we plug in this, what happened? If we plug in this f0 in our form, then we know that here our form is already negative, which means that the Zesky linear form must have had a 0 before this lambda 0, right? And this then means that the first eigenvalue here, which is this min-max thing for n equals to 1, must be less or equal than lambda 0, because there was already, after this move on, there is a 0, right? And we take the minimum of all these zeros. Okay, another thing that we can do with our variational principle is we can compare eigenvalues of the Dirac operator with eigenvalues of sort of associated Schrödinger operator. Let's first, as a toy example, see what happens if we take m1 and m2 to be constant. We call the eigenvalues of our operator t, starting from m1, which was the upper bound of the interval where we have resolvent. So we call them lambda 1, lambda 2, and so on. And b1, b2, and so on, beta 1, beta 2 are supposed to be the eigenvalues of bb star, where this bb star was the operator on the, well, b and b star are the operators in the off diagonal, which are first derivative plus or minus first derivative plus the potential w. So if m is constant, then we just can calculate our quadratic form. Remember that here these m1 and m2 are constants, so we can take them out of these scalar products, and then we are left with something like this. Here we just have the norm of f squared, and here we have b star f squared. And now let us call p of f the zeros of this thing, as always. Now they're easily, they can be calculated easily. Why? Because Well, this here is never 0, so we only need the 0 of the terms here in curly braces. And this is just a polynomial in lambda, and we can just solve. And then we get this. And now if you take this maximum and the minimum over all the f's in appropriate spaces, then since this here is constant, this min max just enters here downstairs in the square root. And this here, this min max gives us the eigenvalues of the operator BB star, which are denoted here by these betas. And then we get the formula that we claim here, that the nth eigenvalue of our Dirac operator is just this. And we just get back the formula for the eigenvalues that we already had before, when we said that m1 equals m2 is equal to constant. It gives us exactly this expression. Okay, now what can we do if m is not constant? This is the interesting case. And here we can at least get estimates. So what we do is, again, we enumerate the possible eigenvalues in this spectral gap of our Dirac operator by lambda 1, lambda 2, and so on. Again, beta 1, beta 2, etc. are the eigenvalues of this Schrödinger type operator, BB star, starting from 0 to the bound of its essential spectrum. Then we also need, before we had, we already had this small mj was the infimum of these mass terms in our Dirac operator. And now we also need the supremum of them, because then we can show that the nth eigenvalue of our Dirac operator is larger or equal than, well, here's something a little bit complicated, and here we see the eigenvalues of the associated Schrödinger type operator. And we also have a bound in the other direction, so a lambda n is less or equal than these here. If, well, here we need this condition, we need some bound which has to do with the bound of the essential spectrum of our Dirac operator. How can this be proved? Well, this is basically proved just as on the slide before. One puts everything in this Schur form, in this Schur quadratic form, and then now we cannot explicitly calculate the zeros, but we can estimate the zeros for fixed x of our Schur quadratic form, and the estimates then lead to these two things. So on the one hand, this allows us to compare the values of the Dirac operator to those of the Schrödinger operators, and it also allows us to compare dimensions of eigenspaces. So here I have two functions, f of lambda and g of lambda. Is not so important how they really look. They depend on m, our mass term in the Dirac operator. We need the supremum and the infimum of these m's. This is quadratic in lambda. And then from this first estimate for the eigenvalues, we get an upper bound for the spectral subspace of our Dirac operator in a certain interval. This is this first estimate here. G of lambda, what is it? Well, g of lambda is this function, and the zeros of this function exactly look like this. So these here are the lambdas where g for given m1 and m2 is equal to 0. This is where this square root and everything comes from, right? So the first inequality here gives us an upper bound for the dimension of spectral subspaces of our Dirac operator in a certain interval, and the second gives us a lower bound, right? Because if I have so and so many eigenvalues before this number here, then the dimension of this subspace is larger or equal than this dimension here. As a corollary from the first inequality here, we get possibly better location of the resolvent set, because before we said m1 up to, what was it? The infimum of this m1 function belongs to the resolvent set of T. In reality, now we know that even to the G inverse of the minimum of the spectrum of BB star belongs to the resolvent set of T. There is also a localized version of the theorem that I just told you. This works like this. So first, let me talk a little bit about Schrödinger operators on an interval, which we already heard in 2 talks. So let's fix a finite interval in R, and we look at B, which is first derivative plus W, and B star, this is then minus first derivative W. Here I wrote down the corresponding domains. What we want is BB star. It turns out it has only purely discrete spectrum, and its eigenvalues are given by such a variational principle here, right? So up here, we basically have only the norm of B star x squared gives this here. If we can control if our potential is sort of nice, so at least C1 up to the boundary of our interval, and if we have bounds for W plus W star, then we get also, I mean, this is a very, very rough estimates for the eigenvalues then of this operator BB star. They just come out from this variational principle. One plugs them in, one estimates a little bit, and then one gets these estimates. Okay. And now we can use this also to get sort of localized comparison theorem for our Dirac operator with Schrödinger operators as follows. We take an interval, we define these operators B sub I as before with the appropriate boundary conditions. Again, lambda 1, lambda 2, etc. are the eigenvalues of our Dirac operator. And now beta 1 sub I, beta 2 sub I, etc. are the eigenvalues of our localized Schrödinger operator here. And now what before was the infimum and the supremum over over these M functions, these mass functions, on all of the real line, we now just take the infimum and the supremum localized in this interval. And then we get upper bounds for the eigenvalues of our Dirac operator. We only, yeah, and we get that then lambda n is less or equal than this thing here. The formula is more or less the same as we had before. Only that instead of here the supremum over all of the functions, we just have the supremum over this function localized to the interval I. And then we also get, oh yeah, I think this should be a larger equal. Because then again, we get a lower bounds for the dimension of the spectral subspace. This dimension here is larger or equal than the corresponding dimension. Again, here we need to change the interval. We basically need to translate of the interval for the Dirac operator to the interval to the corresponding Schrödinger type operator on the interval. And then we can say something about existence of eigenvalues if we have existence of eigenvalues of this bi star in a certain interval. And this basically gives us a recipe how we can construct Dirac operators with eigenvalues. We just need a potential, this M and W, in a certain sense, so that the limit of this W is large. This gives us that this interval where we have a chance of finding eigenvalues is large. And then we also need that the potential W in a certain part of our real line has a deep value, deep enough, so that in these deep values we have enough eigenvalues of this BID star operator, which then lead to eigenvalues of the Dirac operator, sort of. And since this is a localized version of our theorem, we only get lower bounds for our Dirac for the spectral dimension of our Dirac operator. Of course, now we can glue together many of such operators, localized versions. So let's say in a certain space, in a certain part of the real axis of the real line, we have such a value. Then we get an eigenvalue. Further away, we have another one. So we can actually produce as many eigenvalues as we like, finitely many, because we still need that our potentials have a limit if we let x tend to infinity and minus infinity. Now, just to give you an idea, we calculated one toy example. We set here the W function, the off-diagonal one, equal to 0, and we just have this mass type potential. And we looked at 3 different scenarios. So one is this M2 is constant, and M1 here has a little valley. Here, both of them in a certain interval go down, and here they sort of get closer together. And then just from our from these general considerations, we can say where the essential spectrum is. In all the 3 cases, the essential spectrum is the same because this just depends on the limit behavior of the potential to infinity, and this is the same in all 3 cases. And then in the first case, we can have point spectrum only here between this minimum of M1 and its supremum. Same as here. And in this last case, we can have point spectrum up here and also down here. So this is just what I said. So we have in the first 2 cases, we can have eigenvalues only here. And in the second case, we can have eigenvalues close to -m and close to m. And then we did run some numerical calculations. So here you can see, so this is when t, well, this is hard to read, sorry for that. T is sort of the strength, how we perturb our constant mass. And you can see if this strength grows, then we get more and more eigenvalues. The continuous line is what can be calculated numerically. And the dotted line is what we calculated using our min-max principle to give upper bounds for the eigenvalues. And at least for the first eigenvalue is sort of okayish, and then well, it gets weird. Yeah, so these are the different versions for our toy example that we calculated. Also recently there was published a paper by Dasgupta, Khurana, Tahwila, Saleh. They were interested in a one-dimensional Schrödinger operator. They tried to do something like, they call it hydrogenic Dirac operator. The potential is here exponential potential because so this exponential here gives the decay at infinity, and this t factor here makes the potential equal to 0 at 0. These on the right hand side, you see their calculations that they did numerically. To get there, they used a certain, well, they transformed the Dirac operator to a dynamical system. And then in the end, they got these numerical approximations. We could reproduce the graphics for the first 3 eigenvalues, sort of. I mean, it looks the same. We cannot do higher eigenvalues that they got. Well, this gamma is, where is this gamma? This actually appears up here in this. Yes, I think it was up here. Because the hypotheses do no longer hold for our methods, therefore we can only calculate the first 3 eigenvalues. Just maybe 2 words on the Dirac operator and the half-line. In principle, everything works the same, except it doesn't. So if one looks at the Dirac operator on the half-lines from 0 to infinity, again, we have the same assumptions. Our potential here, bounded, measurable, real-valued functions. We still want the gap between them. So here, minus m2 and m1. We want that the limit for x to infinity exists. And then again, we can localize the essential spectrum. It's the next slide. What is the big difference between the real line case? Well, the big difference is what happens at 0, because at 0, in the half-line case, our operator is in the limit. Oh, well, this word is wrong. This should not be here. Is in the limit circle case at 0, which means we need to choose boundary conditions in order to get a well-defined self-adjoint operator. Turns out that, well, that's quite easy to do. This is also well known since a very long time. One just fixes some alpha between 0 and p, and then one says, okay, I want that my function is just a multiple of cos alpha sine alpha. This gives self-adjoint extensions. All eigenvalues still are simple. We can localize the essential spectrum. The problem now for our method is that the operator that we get like this is no longer a block operator matrix. So it does not really apply. We do get a block operator matrix when alpha is equal to 0, because in that case, we just say something about the first, we say something about the second coordinate. This must vanish at 0. If alpha is p half, then it's the other way around. The first coordinate must vanish. And the domain of our operator can still be written as a block operator matrix in these two cases. And well, everything works just the same. Funnily, also for certain alphas, we can get one eigenvalue if there is no potential present, which is not true in the case of all of the real line. In other cases, when alpha is different from 0 and p half, we still don't know really what to do. At the moment, there's work in progress with 2 people here from Colombia, Elison Leguizamón and Hanne Vandenbosch from Chile. Well, we need different methods to say something about cases when alpha is different from 0 or different from p half. So thank you very much for your attention. Questions?
All right, so let's thank Monica for the very interesting talk. So let me stop the record real quick.